Okay, so yeah, the plan today is to tell a story. Okay, I hope most of you would enjoy this story, and towards the end, you'll automatically see why somebody tells this kind of a story in a lecture on Introduction to Engineering. Okay, so this story is set in a village called Konigsberg. Okay, and this is set in 1890, because in the later half, the last decade of the 19th century. So, who all have heard about this town called Konigsberg? So this Konigsberg is famous for many people who actually either were born there or lived most part of their life there. Okay. One of the most important personalities that as computer scientists you will encounter is Euler. Euler is a famous mathematician. He is also considered as the father of graph theory, which is one branch of mathematics that will get used a lot in computer science, because all your networks, now even the abstract networks like social networks, everything gets modeled as a graph. And there is a famous problem called the 7 bridges problem, the bridges of Konigsberg problem, which was modeled across a particular island configuration in Konigsberg. This is considered as one of the first problems in graph theory, and some people consider that as the start of this branch of mathematics called graph theory. That is one very famous person from Konigsberg. Another person, if you have a wide reading, if you read philosophy, one of the towering figures in philosophy is Immanuel Kant. Immanuel Kant also lived in Konigsberg. If you were, followed a bit of what are the famous unsolved problems in mathematics, the so-called conjectures in mathematics, you may have come across this conjecture called Gold-Box conjecture, right? Does anybody know what's the Gold-Box conjecture? What's the Gold-Box conjecture? Please feel free to unmute and speak. So Gold-Box conjecture tells that any even number greater than 2 can be written as the sum of 2 prime numbers. Okay, so this is still an unsolved problem in mathematics. Okay, so what is a conjecture? A conjecture is slightly, it is an unsolved problem for sure, but it is an unsolved problem in which a lot of mathematicians believe that the answer would be a particular way, and then they conjecture that that is true. Okay, so they don't have a proof that it is true. Whether proof is the most important thing in mathematics. Every mathematician is in search of a proof. Okay. Unless you prove it, there is, no matter how famous you are, making a conjecture, it's as good as a random statement, except that it has a lot of fame attached to it, like the Gold-Box conjecture that I just described. So this is due to a mathematician called Christian Goldbach. Goldbach also is from the same town, Konigsberg. So these 3 people that I spoke about are 1 century earlier than what the timeline of this story. They are from the 18th century, like Euler, Kant, Goldbach. They are all from the 18th century. Whereas this story runs in the 19th century, and there is a very, very famous mathematician of the 19th century who is also from Konigsberg. That's David Hilbert. Okay. And this story is, this is surely a cooked up story, a hypothetical story, is about a hotel, okay, about a hotel that is run by David Hilbert. Okay, so with that amount of history, let's begin the story. Okay, so this David Hilbert runs this hotel called the Grand Hillbert Hotel in this town of Konigsberg. Okay. And somehow this hotel is the most popular hotel in the town. And the reason is very simple. This hotel has so far never refused entry to a guest. Okay. It never says the rooms are full. Okay. It's, people think it is so massive, even if there is a football match. And by the way, this Konigsberg is currently in Russia, but it's originally historically a Prussian P. Prussia with a P, a Prussian town. During the time of this story, it was a German town. It was with Germany. And Germans are fanatic about football, right? And soccer or football. So even during, big football matches, this hotel never gets full. even if every team participating, their officials, they all want a room, Hilbert would give it to them. So this was surprising to the other hoteliers, other hotel owners in the town, and they wanted to figure out what is the trick. How does Hilbert manage to never say no to anybody? And since Hilbert is also kind of a slightly adamant, arrogant man, they did not want to go and ask him directly. So instead, they knew, like many old people, he also had a soft corner for children. So the other hoteliers, they found a small kid and sent him to Hilbert to ask this question: how many rooms does your hotel has? Okay. So okay, this child goes and asks Hilbert, how many rooms are there in your hotel? And Hilbert is kind of not interested in the beginning. He says, you may not understand even if I answer. You don't even know what that number is. And then this child is offended. He says, no, I am very good with maths in school. I do all my arithmetic very fast. I know all the numbers. I know a lot of numbers. And then Hilbert asked, okay, what numbers do you know? He started counting, I know 1, 2, 3. I even know 1 million. I know 1 billion. So, right. So then Hilbert gets interesting. Then he asks, okay, I see that you're good at numbers. What is the largest number that you know? And then this child, spontaneously says, I know a trillion, I know a quintillion, and so on. But then Hilbert is just smiling. He's not saying anything. But then the child suddenly pauses and sees, oh, I see, that's difficult, because whatever number I can think of, I can already think of a number that is larger than that, right? When I think of 1 billion, I can think of 1 billion and 1. When I think of 1 billion and 1, I can think of 1 billion and 2. When I think of 1 quintillion, I can think of 1 quintillion and a 1. Right? So now the child kind of gets confused. Okay, and this really excites Hilbert. Okay, so now the child also kind of understands. Okay, there is something strange about numbers. There is no largest number. No matter how many numbers you give, there is still another number left that you haven't given out to anybody. So there is something connecting this and the hotels in the rooms in Hilbert's hotel, and that's when Hilbert has, his time is up, and he says to the child that in Grand Hilbert's hotel there is a room for every number. Okay, so here numbers means counting numbers. 1, 2, 3. That's because the child never spoke about negative numbers, zero, fractions, etc. So this is what Hilbert answered. Okay? There is a room for every number. So the child goes back, and the other hotel owners, they ask him what was said, and the child repeats his answer that in Grand Hilbert Hotel there is a room for every counting number. And some of them understand, some of them don't. There anyway. I mean, those who do not understand, are confused, but some hoteliers at least get what is happening. Okay, so this hotel's success story continues. It is still the most sought after hotel in town. Okay, so that once you have a room for every number, you can even accommodate every person on the earth, right? Now the population of Earth has crossed 7 billion. Maybe at that time it was smaller, maybe half of it, maybe, I'm not sure. So that's no deal for Hilbert's hotel, right? So we are now going into a more imaginary story. Now the occupants are no more going to be human beings. They are going to be more interesting creatures. Okay, so there is a conference that is planned in Germany, in Konigsberg. Okay, this is called the Number Theory Conference. Okay, and we started off by mentioning about Christian Goldbach. So this is Goldbach's town. So this 1882 is celebrating 140 years of Goldbach's conjecture. Goldbach made this conjecture in 1742. The conjecture that every even number larger than 2 can be written as a sum of 2 primes. And the history of this conjecture is also interesting. This conjecture was first proposed in a letter that Goldbach sent to Euler. Okay, and there is a you read Wikipedia about Goldbach's conjecture, it will give you this, the snippets of this letter conversation that they don't have WhatsApp to get an instant reply, right? So it's more about written letter conversation that happened between Goldbach and Euler. Yeah. So this number theory conference, was held to celebrate 140 years of this Goldbach's conjecture. And who attends number theory conferences? Okay, this is a cooked up story, as I already told you. It's all the counting numbers, 1, 2, 3, 4, 5, etc. All of them come for a conference, and they're all very particular. They want single occupancy rooms. Okay, they are not going to share their room with anybody else. And being the largest hotel, the natural choice to accommodate all the participants, these numbers in the conference, is the Grand Hillbert Hotel. Okay, and you're sure, right? I mean, Hilbert can actually do that. All he has to do is ask, put each number in the room number that is corresponding to that. Okay, so the participant named 1 will go to room number 1 and so on. Okay, so that's what Hilbert will do. Okay, in fact, Hilbert also has this notion of what is an algorithm. Okay, instead of repeating something over and over again, he tries to codify it into a small set of instructions. In this case, it's a single instruction, right? It says Frau X. Frau is German for Miss. So Miss X, please occupy room X. Okay, that's what this rule says. And in fact, Hilbert, being a mathematician, has this notice board kept in front of his hotel, not in the lobby of his hotel, not in front of the hotel, where the room number, the guests, their room numbers are displayed. This is common in many hotels. You have the name of the guest and the room number in which that guest is staying. But Hilbert, being a mathematician, and also, even though computers were not available at that time, people had the idea of computing. Computing is much older than computers. In fact, adding two numbers in place value notation is an algorithm. Even though people were doing it by hand, it was an algorithm. So he had this notion of computing. In fact, one of his biggest open problem was, can every mathematical problem be given a algorithm-like procedure, a finite procedure to solve it, which was later disproved by Gödel and so on. But anyway, that's another story that will make actually a very interesting presentation on its own. But today we will stick to our story. Okay, so this is how Hilbert kind of optimizes his notice board. He'll just put a rule like this. Okay, Miss X occupy room X. So everybody is happy. The conference starts. Conference is about to start, and then there is unexpected event. Okay, and this unexpected event is, you see suddenly a new guest. Okay, she calls herself Zero. Okay, and she's from India, obviously, right? I mean, that India, one of the from ancient times, one of the most important contributions of India to mathematics is the discovery of a symbol for zero. By the way, the place value notation is also a discovery from India. Maybe this is equally important. I don't want to compare which is more important, but India introduced this number zero. Okay. It's still not sure what is the how long ago Indians started using this symbol zero. Lot of people, till maybe something like 10 years ago, the earliest known inscription of zero was what you see in the bottom of the screen, this Chaturbhuj temple in Gwalior. Okay? And this was like 900 CE. This inscription which had zero, but a parchment was leaf parchment, which is probably much older, but it's still, the carbon dating is still not conclusive. It is somewhere between 200 CE and 900 CE, also has this inscription of zero. So depending on how the carbon dating would actually turn out, it will change as to which is the more earlier record of a zero. In fact, this is actually one reason why history is also, even though some people think history is studying about what already happened, there is a lot of how do you say, thrill and mystery in as to how people make these historical information available, right? How do you figure out what happened when and so on? So this is one such example. The jury is still out as to which is the earlier document, and more importantly, that will tell how old zero was being in use. Okay, this Bakhshali manuscript is from Peshawar, present-day Pakistan. Okay, by the way, this Bakhshali manuscript also contains a lot of rules for carrying out many computations, like solving systems of linear equations, solving quadratic equations, rules about finding the the number in arithmetic progression, arithmetic or geometric series, etc. Right, and these are all kind of given as in a modern day language we would call them algorithms to solve quadratic equations, algorithm to find the nth number in an arithmetic progression, and so on. But as I told you, the word algorithm was not in place. Computing was not in place. The word algorithm is actually from Arabic. It's named after a Islamic mathematician, Arabic mathematician called Al-Khwarizmi, if I remember correctly. Okay, so yeah, so this is the story of Zero, but in our story, Zero has a different role, right? I mean, she suddenly turns up in the hotel, and unfortunately, all the rooms in Hilbert's hotel are occupied because you have infinitely. The Hilbert's hotel had one room for every number, and they are all occupied now. So, what does Hilbert do? Anybody wants to make a guess? We want to help Hilbert. You have infinitely. The Hilbert's hotel had one room for every number, and they are all occupied now. So, what does Hilbert do? Anybody wants to make a guess? We want to help Hilbert.
He shifts each number to the next room, x plus 1.
Exactly. Excellent. So this is what Hilbert would do. He'll go up to his stairs. He has this megaphone. Okay, so this megaphone is an instrument that amplifies sound, and this particular one I think is a megaphone that was kind of made by Thomas Alva Edison. Edison is also kind of a contemporary, but okay, I think we are mixing too much of history into a story. Okay, and he makes this announcement. Dear ladies, there is an unavoidable situation. We request each one of you to shift to the next room. Okay, so this is what Hilbert does. And now, where does Zero go? Zero goes to room number 1, because 1 who was occupying room number 1 has now shifted to room number 2. But 2 is empty because 2 has shifted to 3. 3 is empty because 3 has shifted to 4, and so on. Okay, so Hilbert manages to save the night, and things are going okay. The next day, once Hilbert goes down, he corrects the notice board. Earlier it was fro x assigned to room x. Now it is fro x assigned to room x plus 1, as pointed out here. Okay, so the conference starts on day 1, and while the conference is on, okay, Hilbert is hit with a much bigger surprise. Okay, there is a whole train of numbers arriving from China. Okay, it's like 24 hours late to arrive for the conference. China is far, so it took a long time for this train to arrive, and it has numbers -1, -2, -3. Okay, why did I say that this train is from China? Because again, the earliest known use of negative numbers is from China. It's from at least the first earliest known written record is from this book called 9 Chapters on the Mathematical Art, which is dated to somewhere between 200 BC and 50 AD from China. Okay, some of you may have noticed that negative numbers are actually earlier than 0. Okay, 0 was around 900 AD, 900 CE, if you remember. This is 1,000 years at least older. It's not that surprising, okay, because 0 is a more difficult, more abstract concept to grasp than negative numbers. Usage of 0 as a number, usage of 0 as a symbol in a place value notation, that's conceptually a bit harder than thinking about negative numbers. Negative numbers at least comes when you start lending money and so on. Most of these early arithmetic was discovered for applications in trade. So negative numbers are more natural. By the way, fractions are even more natural than negative numbers. Fractions have a much longer history. They were known even to the Egyptian civilizations. They used fractions. The Egyptian civilization is like, what, 2,500 or even 3,000 BC, right? So it's as old as that. So even though in schools, I think we study it in a different order, right? In schools, we first study positive numbers, then 0, then negative numbers, then fractions. Historically, it was discovered in the opposite order, and I think there is no surprise that it was discovered in that order. Okay, for trading, fractions is also like very natural to come up when you're talking about trade. Okay, but back to the hotel. How does Hilbert solve this problem? Okay, now all the negative numbers, there are infinitely many of them. If it were only like, let's say 10 numbers, you could have used that megaphone trick once more, right? You could have shifted X to some X plus 11 and then freed up some first 10 rooms and given it to the 10 new numbers. But what do we do now? Anybody wants to help Hilbert? But what do we do now? Anybody wants to help Hilbert? This is a tougher question. Okay, would you be able to answer if I say that Hilbert actually succeeded?
Sir, minus X goes to room adjacent to plus X.
Okay, then what does X plus 1 do? Because X plus 1 is now occupying the room next to X, right? You're on the correct track, by the way. Anybody? Okay, but what was said? I'm sorry that the screen is not popping out who is speaking, so I did not even notice the name or the number. But that's a good attempt, and that's Hilbert actually builds on this attempt to solve this problem. Okay, remember, all the guys were actually the positive numbers and 0, which came before on the last day, are already at the conference. Now all the rooms are empty. So Hilbert goes and changes his notice board, erases and writes a new rule in the notice board. Okay, and this is the new rule. Okay, now see if you can figure out what this rule means. Okay, so now this is a conditional rule. Okay, in the sense that the room, when Miss X walks in, she has to first check a condition about herself. If she is 0 or positive, then rule 1 applies. That means she goes to room 2x plus 1. If she is negative, then rule 2 applies, the rule on the last line. That means she'll go to room minus 2x. Okay, so for example, 0, rule 1 applies, so it is twice 0 plus 1, which is 1. So 0 will go to room 1. Actually, there is no change. She was already in room 1. What about 1? 1 was earlier occupying 2, but by now the new rule, she has to occupy 2x plus 1, which is 3. So 1 goes to room 3. Whereas minus 1 is now taking room 2, because minus 1, since x is less than 0, the second line applies. So she goes to minus 2 times minus 1, which is plus 2. By the way, there are no rooms numbered with negative numbers. So you cannot go to something like, room minus 2 or anything. So minus 1, fortunately, minus 2 times minus 1 being 2 goes to room 2, and so on. Okay, so you have to actually check 2 things, okay, and convince yourself that both of them are correct. Firstly, that every number, negative, 0, or positive, all of them get a room. And secondly, you should convince yourself that no room is given to 2 people, okay? Everybody gets a room for themselves. And secondly, you should convince yourself that no room is given to 2 people, okay? Everybody gets a room for themselves. Okay, if anybody is not convinced, please shout out. By the way, you would have learned enough of mathematical terminology in your higher secondary, in your 11th and 12th, to know that what we are giving here is a function, right? In fact, this notation, this arrow with a vertical bar in the beginning, is a symbol that people use to represent mappings or functions. Okay, so you know that a function is a mapping from one set to another. The first set is called the domain. The second set is called the codomain, and it obeys 2 rules: that every member of the domain is mapped to a member of the codomain, and unique. The second condition says that it's mapped only to one member of the codomain. So function is a special kind of relation. And in this particular context of the Grand Hilbert's hotels room assignment, what is the domain? Hotels room assignment. What is the domain? Anyone?
All integers.
All integers.
Yeah, it's the set of guests. Okay, you're correct. It's all the people, or in particular, the set of guests. the set of people who are requesting for room in the hotel. What is the codomain?
Number of
Rooms.
rooms.
Exactly. The codomain is a set of rooms in the hotel. So this, what Hilbert is actually writing, Hilbert being a mathematician, what he's writing on the notice board is actually this mapping from guests to rooms. Okay. And can anybody guess what does this, in mathematical language, what would this condition of single occupancy be called? Mathematical language, what would this condition of single occupancy be called?
1, 1.
Yes, this exactly means you're only allowed to write a one-to-one function. Okay, one-to-one functions are also known as injective functions. So if the rule that Hilbert writes on the notice board is one-to-one, then you can be sure that everybody gets a single rule. By the way, we never insist on that, but if the rooms are full, okay, in this particular case, actually the rooms are full. If all the rooms are occupied, that's what I mean when I say rooms are full, then what do you call such a function? But if the rooms are full, okay, in this particular case, actually the rooms are full. If all the rooms are occupied, that's what I mean when I say rooms are full, then what do you call such a function?
Surjective. Onto.
Okay, onto is the more correct word. Okay, onto or surjective. If a function is both injective and surjective, then it's called a bijective function. Okay, so remember, as far as Hilbert is concerned, he only cares about the function being injective, one-to-one. Okay, it's in fact better for him if it is not onto, if it is not surjective, because that means there are still vacant rooms, right? So that is to his advantage. So remember, always in this notice board, Hilbert being a mathematician, what he is trying to write is a mapping which will correspond to an injective function from the set of guests to the set of rooms in the hotel. And the set of rooms being, we know that there is a room for every number. The codomain can be equivalently thought of as the set of natural numbers. Okay, so the in mathematical language, this story or this room assignment is all about finding injective mappings into natural numbers. Okay, yeah. So I hope all of you verified that this function that is written here is indeed an injective mapping from the set of integers, because now you have the negative numbers, 0, and the positive numbers. So your domain, okay, the first set, your domain is a set of integers, and your codomain, as we said, is equivalent to the set of natural numbers. So what I'm asking you to verify is that what you see on the notice board is injective mapping from the set of integers to the set of natural numbers. I hope all of you have verified that. Interestingly, it's a very counterintuitive thing, okay? Because you think that there are twice as many integers as natural numbers, right? But you see that you can kind of fit in integers into natural numbers without any collision, without no two integers competing for the same room, asking for the same room. Okay, so this never happens in a finite scenario, right? Like if you have a set with 10 elements, that take it as the domain, and a set with 5 elements as the codomain, you wouldn't be able to fit these 10 elements in an injective fashion, in a one-to-one fashion into 5 rooms, right? So something counterintuitive is happening in the world of infinities, right? It looks like there are many more integers than natural numbers, but due to this kind of a magic, you can really accommodate integers inside of natural numbers. Okay, so yeah, so this is the number theory conferences story. Okay, if there are any doubts, please ask. Otherwise, we will move to the next scene in the story. Anybody wants to guess what would be the next scene in the story? What conference will you hold?
Fractions.
Great. That's the next story. It's called the rationalist conferences. Okay, rational numbers. Okay, rationalist conference. Okay, this, as I told you, this fractions were known to Egyptians. It's at least 3,000 years older than negative numbers and so. Okay, so we. By the way, do you know why this name rationalist? Okay, so that's a Greek story. why they are called rational numbers, because the Greeks, Egyptian civilization is much older than, I think the Greek civilization is, I'm slightly getting confused with dates, but I think Greek civilization is around 2000 BC, Egyptian is around 3000 BC. So Greek civilization, but Greeks lasted much, Gaul and all were 50, right? Yeah. But anyway, the Greeks, Pythagoras was 300 BC. Yeah. So Greek civilization is, 2000 years old. So that's around the BC AD mark that this Greek civilization is. Pythagoras is around 500 BC. Euclid is around 300 BC. So that's the time, at least, when the mathematics in Greece, in the Greek civilization, was very prominent. And it is during the Pythagorean time, people believed that any number can be written as a fraction, P by Q form. But it was Hippasus. Okay, it was he was from the Pythagorean school, a mathematician called Hippasus, who first discovered that there are numbers. It's not root 2. It was root 2 because which he kind of stumbled upon while thinking about pentagons, side of pentagons, and so on. That there could be some numbers which can never be written as a ratio of two integers. Okay, so that was the that discovery kind of shocked the other mathematicians. Most of the other mathematicians could not really accept that. So they said it's not a rational argument what this guy is making. And that is how, the numbers which could be represented as fractions were called rational, more reasoned out and so on. But now we know that, it is a historical blunder. Okay, there is nothing irrational about irrational numbers. Okay, in fact, they are so abundant. There are so many important irrational numbers, and there are so many irrational numbers. Okay, but the name somehow, comes from there. By the way, our usual definition for a rational number is something which can be written as P over Q, where both P and Q are integers and Q is not equal to 0. I'm slightly changing it without losing anything. I'm going to insist that Q will always be a positive integer. Okay. Why do I say that I don't lose anything? Because if Q happen to be negative, I can shift that negative sign to the numerator. Just flip the sign of the numerator and it would still evaluate to the correct thing. Further, I will actually assume that P and Q are written such that there are no more common factors left. Okay, their greatest common divisor is 1. This is the same trick that you would have used when you studied the proof that root 2 is rational, right? This I think most of you would have done in school, right? How do you prove that root 2 is rational, right? You assume the contrary. Okay? It's a proof by contradiction. You assume that root 2 was rational, and hence it can be written in a form P by Q. And you can further assume that P and Q does not have any common divisors, cancel them out if they have, right? So represent them in the simplest form as P by Q, then square them and you will see that P squared by Q squared equal to 2, which means if anyway, and P and Q both cannot be even numbers because then 2 is a common factor. But now Q squared happens to be twice P squared, which is an even number, which is impossible because Q is odd. That's the proof that root 2 is irrational, right? So this way of representing numbers without any common factor other than 1 between numerator and denominator is something which I'm assuming most of you would know. Okay, but back to our story. Can all the rational numbers be accommodated in Grand Hilbert Hotel? Anybody wants to help Hilbert again here? Back to our story. Can all the rational numbers be accommodated in Grand Hilbert Hotel? Anybody wants to help Hilbert again here? Okay, at least give me a yes or a no. Back to our story. Can all the rational numbers be accommodated in Grand Hilbert Hotel? Anybody wants to help Hilbert again here? Okay, at least give me a yes or a no.
Yes, sir.
You can even
Yes,
type
sir.
that in the chat. Yeah. Who said that? Sorry, can you repeat?
Yes, sir, he can, sir. Me, Manish.
Yeah. How?
No idea, sir, but he can, sir.
But then, yeah. So you are making a conjecture, right? You are not giving
Yes,
me a
sir.
proof.
Yes,
Yeah,
sir. Yes,
but
sir.
Mhm.
Sir, shall I try?
Sir,
Yes, please.
Sir, my guess would be first in room 1 placing the 0 and all the rational numbers between 0 to -1 can be placed first and then placing -1.
No, because already, between 0 to -1, there are infinitely many rational numbers, right? Even if you take rational numbers of a particular form, like 1 by n, you have 1 by 1, 1 by 2, 1 by 3, 1 by 4, everything, they are all between 0 and 1. They themselves will fill up the rooms. And you have things like 2 by 3, which is not given a room already, even within the numbers between 0 and 1. In fact, there are infinitely many rational numbers between any two natural numbers.
sir, sir, if we ignore the negative numbers and if we only focus on the positive numbers, 1, 2, 3. So, like if we take 0 to 1, for example, there are in between there is actually comes 1 by 2, and like that in between 0 and 1 by 2 there will be 1 by 4. So, in that way, if we segregate them, then it may be possible to accommodate all of them.
No. Actually, again, the same problem, because if you try to segregate them, even one group that you are thinking of is infinite, they will occupy all the rooms. They'll fill up the rooms. Anyone else?
I think he cannot fit the rooms.
Okay, that's another conjecture. So now we have two conflicting conjectures. But why do you think we cannot fill?
Because there are infinite rational numbers between any two integers, right? So we are getting the infinite number even in the beginning itself. So infinite number in the sense the entire thing may be filled up.
Okay. I was trying to see who was the speaker, but I'm unsuccessful. Anyway. Yeah, but that's continue.
So, but some infinities we can say that which are smaller than the other infinities. Like in infinities between 0 and 1 will be definitely less than the infinities from the natural number. So it can be accommodated into the.
Why do you say the infinities between 0 and 1 is less than the infinity of natural numbers?
So because if we have 0 and 1, if there are infinite numbers between 0 and 1, then that will also come into the infinity of from 0 to 2 and so on till 3 and like that.
Oh, so you're saying okay, but then you see, even the earlier conference, right? You had this integers which looked almost like double as natural numbers getting accommodated within natural numbers, right?
I think we won't be able to fit because we won't be able to tell the. I mean, if you're filling numbers between 0 and 1, we won't be able to tell the number 1 which room to go to.
Okay.
Sir.
Yeah. Yes.
Sir, I have a proof, sir.
Yeah. That's the most interesting thing, right? Most prized thing is a proof. So tell me.
So if one room is arranged in a parallel way, that is, if one.
What do you mean by a parallel way?
So,
don't do that. Don't do that. Yeah.
Yes, sir. If 1 to 100 is a room, sir, opposite that there is 1 to 100 rooms, sir. Like that, they are infinity, sir. Here, it will become a square, sir.
But you don't. You are not allowed to bring in an engineer and change the the hotel, right? There is no more construction allowed in the hotel.
Yes, sir. We can assume like that, sir. We can fill from the rational numbers from 0 to 1 to 1 line, sir. And from 1 to 2 in other line. It will be natural numbers.
Yeah, but then you don't have that many. But how do you arrange? Yeah, actually, your answer is partially correct. Okay. Yeah, but your answer is partially correct. But the gap in your answer is like, how do you now your rooms in the Hillbert's hotel are more like a line. 1, 2, 3, 4, etc. How do you still make them a square and actually fill it up? Your the rooms in the Hillbert's hotel are more like a line, 1, 2, 3, 4, etc. How do you still make them a square and actually fill it up? That's the question. But I kind of know that you have a feel for it, so your answer is correct. Okay, but this is not what Hilbert actually proposes. Hilbert proposes this rule. Okay, this is what is there in the notice. Okay, and I want you to spend 2 minutes thinking about this rule. Again, this is a conditional rule. It depends on the sign of the numerator. If the numerator is 0 or positive, you have to go by rule 1. If the numerator is negative, go by rule 2. Remember that the denominator would always be positive. And again, we kind of represent the numbers in the simplest form. There is no common factor between P and Q.
Sir?
Yes?
Why these numbers, like why 2, 3, and 5?
Very good. Okay, the answer is that they are prime numbers. Actually, any 3 prime numbers would have worked. I could have taken 11, 13, and 17. 11 to the power P, 13 to the power Q, and rule 1, and 11 to the power minus P, and 17 to the power Q. But it's important that they are prime numbers. We will see why.
Sir, who will occupy room 1, sir?
Very good, very good. Okay, so if you see at the corner of the slide, you see that nobody is occupying room 1. So remember our discussion 5 minutes ago. That's not Hilbert's problem. In fact, Hilbert is happy if some rooms are vacant. So in this case, room 1, 2, etc. will be vacant, which is okay. You're not looking for an onto function. You're not looking to fill up all the rooms. Yeah. Ask me. I mean, it's a very
Y0 will occupy room 3, sir.
Very good. Okay, so 0 can be in the simplest way you can write 0 is 0 over 1. Okay, so 0 over 1 means P is equal to 0 and Q is equal to 1. So since P is 0, rule 1 applies. So it will go to 2 to the power P, 3 to the power Q. So 2 to the power 0, 3 to the power 1, which evaluates to 3. Similarly, in the picture, it's also written 1 goes to room 6 because 1 is 1 over 1. Okay, 1 by 1. So it is 2 to the power 1, 3 to the power 1, which is 6. But I still haven't got the most important question. What should be the most important question to ask here? Anyone?
If both the rooms
accommodated.
Yeah, firstly, does every number gets accommodated? But that seems to be right. I mean, every number either has numerator 0 or non-negative or negative. So they get a room. They can just do this calculation. All you have to worry is that whether the calculation will give a natural number, because a counting number, because Hilbert's hotel only has rooms which are labeled with counting numbers, right? But if you know that both P and Q, in the first rule, P and Q are positive or 0 or positive integers. So 2 raised to P, 3 raised to Q is a natural number. No issue. Similarly, in the second case, if P is negative, then minus P is a positive number. So 2 raised to minus P, 5 raised to Q is a counting number. Okay, you are never going to have something like 2 raised to minus 4 or 2 raised to minus 1 even, right? Because it is minus P when P is negative. So the result is always a natural number, and hence every rational number gets a room. What is the second most important question?
Do the rooms collide? As in, this one room.
Exactly. Does everybody get a single room? Okay. Is there is the function injective? Is the function one-to-one? What is your guess?
Yes, sir, they are.
Yeah. Why is it injective?
So because if you see the first, it is like a GP which involves the multiples of 3, and the next one is 5. They don't collide.
Correct. Actually, you're correct, but the most the cleanest way to see this is that this follows from the fact that prime factorization of a number is unique. Okay. So in fact, if you tell me a room, I can tell who lives there. Like, no, you tell me that the room is 6. then I already know I prime factorize 6, it is 2 into 3. So it is 2 to the power 1, 3 to the power 1. So it is 1 by 1 which leaves there, and it's only 1 by 1 which leaves there, because there is exactly one way to prime factorize a number. Prime factorization is unique. This is, by the way, known as the fundamental theorem of arithmetic, that every counting number has a unique prime factorization. But say if the room was 10, then let's say 20. If the room was 20, then it is 2 squared into 5 to the power 1. So since it is rule 2, it would be minus 2 over 1. Minus 2 will be living in room number 20, and minus 2 alone will be living in room number 20. Who will live in room number 7? Nobody, because only rooms, the only rooms that will get occupied are those which can be written as 2 to the power something times 3 to the power something, or 2 to the power something times 5 to the power something. These are the only rooms that will get occupied. But as we mentioned, nobody wants to insist that all the rooms are full. Okay, so this is also done. Okay, now any doubts here? So Hilbert succeeds. Okay, so there are only rational numbers are, though they seem so much more in number. Between every natural number there are infinitely many rational numbers, but still all these rational numbers can be comfortably accommodated inside natural numbers with lot of rooms to spare. Okay, so the infinity of rational numbers is really not bigger than the infinity of natural numbers. Rational numbers is really not bigger than the infinity of natural numbers. Okay, so any comments here? Any comments, questions? If not, does anybody wants to? Yeah, the next conference is slightly difficult to guess. Okay, so let me. Next scene is the language conference. Okay, so I think I'll go over this a bit fast. Okay, so this is again to celebrate 120 years of Humboldt. Humboldt is also a famous German scientist. The concept of modern university owes a lot to Humboldt. Okay, so in a language conference, let's say all the novels are what participates. Okay, but not just novels that has already been written. It's all the novels that can possibly be written. It's like the number theory conference in example, right? Because if you think about all the natural numbers that were already written by some human being, that's a finite collection. The natural numbers become infinite only when we talk about all possible numbers that can be written. Similarly, in this language conference, we are talking about all possible novels that can be written, and hence it's an infinite collection. The question is how infinite it is. Okay, so in fact, I think this sentence is from Humboldt himself on whether language is finite or infinite. Okay, so this language is something which if I had, I see that I have only 10 minutes left, so I don't want to digress too much into the importance of language in the evolution of human intelligence. But the language, almost most of the scientists believe that the capacity of humans that really differentiates human beings from any other being on earth is its capacity for language. And in particular, what is so special about language? What is so special about language is that using a small set of rules, right? In fact, the words in any language is finite, right? Like almost every word in English is captured in the Oxford Dictionary. There may be something like 100,000 words, but you can create infinitely many sentences. Every creative person comes up with their own new sentences, their own new novels, meaningful sentences, right? So that's the power of language. With a finite set of resources, you can create an unbounded collection of ideas and so on. Okay, so this power of language is this is the power that makes language so special. Yeah, but let me not digress too much and let me rush into it. So even though, so let's say all the novels come into this hotel, all possible novels. Do you think Hilbert will be able to accommodate them in the hotel? By the way, remember that novel you can even think of as a collection of strings, right? Like English alphabets, punctuation marks, and so on. So in some sense, these are, and every novel has to end somewhere. So these are finite strings, okay? Finite strings of languages. Strings include new line breaks, punctuation marks, everything. So how many will all such possible strings, even meaningful, non-meaningful, we don't mind, can they be accommodated in Hilbert's hotel? So the answer is yes, okay? And the rule is something very similar to what we did for rational numbers. There were only like p by q, so we used only 2 prime numbers for positive rational numbers and a third prime number for the negative rational number. Here we may have to use an unbounded number of prime numbers, 2, 3, 5, 7, 11, 13. In fact, you will use as many prime numbers as the length of the string, okay? Now, what is written here, unlike the previous examples, is not the full description of the function. That's because when you can write it on a notice board, but it's a bit clumsy. So what is given here is an example. And from this example, I want you to guess what is the rule. Okay, so your turn. Can you guess what is this mapping? So here the string that you're trying to encode is a space book. And the room number that this guy will go and stay is what is written below. 2 to the power 1, 3 to the power 0, and so on. So here the string that you're trying to encode is a space book. And the room number that this guy will go and stay is what is written below. 2 to the power 1, 3 to the power 0, and so on.
The power is itself the, when we write the alphabets, the A is in first position and the space is in 0 position and B is in
No. Oh, you mean okay. Yeah, you're correct. Okay, but here just be careful with the word position. So there is the position of a letter in the string. Like in this case, B is the third letter. The fourth and fifth letters are both O. K is the 6th letter, and so on. So there is a position in the string. And secondly, there is a rank in the alphabet. So here I consider space to be rank 0, A to be rank 1, B to be rank 2, C to be rank 3, and so on. O will turn out to be rank 15, K will turn out to be rank 11, and so on. Okay, so what is this example tells you that you are going to have a string of prime numbers where if the string to be encoded had something like length 100, you will take the first 100 prime numbers, and each prime number would be raised to the exponent, where the exponent is the rank of that particular symbol in your chart. Okay, is that clear? If you did not understand, please ask. Okay, and here also I claim that this is an injective function. Every string will get a number because it's just a multiple of prime numbers, and hence it's a number. It is injective again because of the unique factorization of prime numbers. Okay, if you know two strings, because if two strings are different, that means at least in one position they have a different character, which means that corresponding prime number's power is different, which means the resulting number would be different. So that ensures injectivity. Okay, now this conference happened a century ago. If it was a modern day story, instead of a language conference, maybe I would have made it as a programmers conference, right? And I would say that a C programming conference, and I would say that every C program comes to the hotel, comes for this conference. So can we accommodate every C program in Grand Hillbert's hotel?
Yes, sir.
Yeah, the same rule, right? A C program, after all, is a string of ASCII characters. If you open a C program in a text file, that's what you really see. And there are 256 ASCII characters in total, but maybe that number doesn't matter. Instead of the English alphabet, which is 26 small letters, 26 uppercase letters, and some punctuation marks, in ASCII characters, there may be something more like hash and dollar and some extra symbols, which also you have to encode. But exactly the same pattern you can use to encode them also. 1 second. Okay, sorry. Then, yeah, oh, this I should have asked you to guess. Okay, I got distracted with my dog barking here. So this is the next conference. Okay, this is the real conference. Okay, who goes to the real conference?
Real numbers.
Great. Okay. And the same question. This conference happens in 1891. Okay, there is a significance to 1891, which we will see in a couple of minutes. Okay. So, and what is the question? Can all the real numbers be accommodated in Grant Hilbert's? Okay. What is your guess? Remember, all the rational numbers could be accommodated. In the interest of time, let the story go on. Okay. So this real number conference is organized by this very famous mathematician called Georg Cantor. Okay. Cantor is contemporary of Hilbert, actually 20 years older to Hilbert. Okay. And he is the one who wants to organize this hotel. And he is a very, very good mathematician. And he kind of has a suspicion. He thinks that Hilbert may not be able to accommodate all the real numbers in his hotel. Okay. So he approaches Hilbert, and Hilbert is kind of, as we mentioned in the beginning, a bit of an adamant person. So he says, yes, he can accommodate all the real numbers in the hotel. Cantor argues, no, you cannot. Hilbert, by now everybody knows what is the number of rooms in Hilbert's hotel. So Hilbert now doesn't keep it as a secret. He says, I have infinitely many rooms, so don't worry. But then Cantor says, no, that infinity is not enough for me. There are much more real numbers than rooms in your hotel. And then Hilbert is kind of offended. He says, no, nothing is more than infinity. And Cantor says, no, my infinity is more than your infinity. Okay. And then Hilbert is really agitated, and he said, you just send them in, I'll accommodate all of them. Okay. And then Cantor sends all of them. Cantor sends all of them to the hotel. And and Hilbert claims to have accommodated all of them, but now Cantor is not sure. Cantor has a feeling that maybe Hilbert is playing some trick on him, and but he knows that in Hilbert's hotel, checking whether everybody is occupied, everybody got a room and a single room is very easy, because Hilbert has this habit of writing the rule in the notice board, which is very easy for a mathematician to figure out whether it corresponds to rule of an injective function, right? So Cantor next day goes and checks the notice board, but to his surprise, he sees that the notice board is empty. Hilbert hasn't written it. Okay, so Cantor is a bit surprised. Okay, and then he asks Hilbert, "Why is there no rule?" So then Hilbert said that, as you also know, this is a much more complex problem, and I discovered a very, very interesting rule. But I first want to publish that rule in my name, and I don't want to make it public straight away. So I am keeping it as a secret. Okay, so he's saying I have a rule, but it is so precious, so I'm keeping it a secret. Hilbert is not convinced, and Hilbert asks, if that is the case, right? So that's what Hilbert says. Every real number has a room. Cantor says, but there is no rule. Hilbert says the rule is too precious for the board, and Cantor asks, how does he check? So Hilbert says, okay, you pick any real number that you want, and I'll show you where she is placed. So Cantor just tries, pi, and you see that pi is in. Hilbert says, okay, pi is in room number 2. Cantor asks, where is cube root of E? And Hilbert takes him to room number 65,537, and there it is. Cube root of E is staying there. But this is getting tiring. Okay, Cantor is getting tired. Cantor is an old man by then. He is getting tired. He says, no, this is too much, right? This is not. This is too tiring. Then Hilbert asks, okay, so that means you give up. Do I win? Cantor says, no, I'll get back tomorrow. I'm tired now. But can I use your notice board to leave a message? Okay, and Hilbert agrees. Okay, and then Cantor writes a message and goes back. What's the message that Cantor writes on Hilbert's notice board? This is the message. Okay, please read this carefully. If you are staying in room number I, and your ith digit after the decimal point, all real numbers have a decimal representation, right? In fact, yeah, you look at your ith digit. If you are staying in room number 9, look at the 9th digit after the decimal point. If you are staying in room number 10, look at the 10th digit after the decimal point. And if it happens to be 5, okay, if when the 9th room guy looks at his looks at her 9th digit after the decimal point, and if that turns out to be 5, then she has to contact Hilbert urgently. During the conference, she has to go and meet, sorry, not Hilbert, to contact Cantor urgently. This is the notice that is there in the board, right? Looks very suspicious, right? What is Cantor trying to do? Right. So this happens, and assume that everybody reads this notice and does as it is suggested. Okay. Then the next day, Cantor comes to Hilbert's hotel and says, okay, now I have a number, a real number written, real number with me, and I want you to show where she is placed, okay, which room she is placed, okay. And Hilbert asks, okay, what is the number? Cantor gives this number, something which looks like Miss 0.5555655556566, right? And Hilbert says, yeah, I was tricking, you win. Any guess how this happened? Looks like a kind of, a suspense thriller, right? How does suddenly, last day there was pi, there was cube root of e, there were so many numbers tried out. Hilbert could show them all where they were staying, but this particular number that Cantor said, Hilbert even did not look, because Hilbert really understood that Cantor found an argument that that would defeat. Okay. So again, in the interest of time, let me not pause. Let me go ahead and tell what was Cantor's trick. Okay, how did Cantor really create this number that you saw on the previous slide, this 0.5566655, etc. So let us say root 2 was staying in room 1. Okay, then root 2, since it is staying in room 1, will look at the first digit after its decimal place. So that is 4. So the instruction on the notice board, remember, said that if that ith digit was 5, then you report. But here the ith digit is 4. So root 2 will not contact Cantor. Since room 1 did not contact Cantor, in Cantor's number that he is noting down, his first digit after the decimal point will be 5. Okay. Now, room 2, let's say pi was staying in room 2, then pi will not look at the first digit after the decimal point. It will look at the second digit after the decimal point, and that is 4. Again, it is not 5, so pi will not contact. So Cantor's second digit will also be 5. Room 3 was 0. 0's third digit is not 5, so 0 will not contact. Similarly, room 4, let's say, was occupied by E. It is fourth digit is 2. It will not contact. Here is the first guy who will contact. Okay, root 3 is staying in room 5. Since it's in room 5, it should look at its fifth digit, and yes, it happens to be 5. So 5 will contact Cantor, and if somebody contacts Cantor, that digit Cantor will make 6. Okay, so if the guy did not contact, Cantor will write 5. If the guy contacted, then Cantor will write 6. That's the idea.
Sir, so why only 6, sir?
He could have written anything except 5, but let's make it keep it a bit simple, and Cantor would write 6. Okay.
Sir, why root 3 is in room 5?
No, so yeah, so this is like a suppose. Okay, I'm only kind of giving an example. So Hilbert claims that he has put every real number in a row, and all of them come and read the notice board. And I mean, this is just to show you an example. Room 5 could have been any real number, but that real number will check whether its fifth digit is 5. If it is so, it will report to Cantor, otherwise it will not. And based on that, Cantor will create his number. If the arrangement of the numbers were different, Cantor's number that Cantor created would also have been different. This is only an example, just to illustrate what Cantor actually did. So this assignment is hypothetical, right? In the sense, whatever was the assignment, Cantor could have created one such number. It may be a different number based on the assignment. Is that clear?
Yes, sir.
Okay. Now this is the number that, yeah, ask me. Okay, so this is the number that Cantor created.
Is this the only number, sir?
No, there are many more, but I mean, we are only saying what is Cantor's trick, right? This is not the only answer. In fact, I'll talk about how many answers Cantor actually has. Okay. In fact, for anybody who did not, who contacted, instead of 6, you could have written 7, 9, anything other than 5. Yeah. Okay. But I'll come to that. Okay. I don't want to jump the gun here because this is the most difficult part of the talk. So I want to make sure that you understand one example before jumping into other possibility. Okay. Yeah. So this is the number that Cantor actually noted down and brought to Hilbert the next day. Okay. Now, why did Hilbert say? Why did Hilbert lose the game? Okay. Why is it that this number was sure not to have been given a room? Okay. Yeah, so here goes the proof. Okay. Suppose this number was given room 1. Okay. But then the first digit of this number is 5. And why is it 5? Because the guy living in room number 1 did not report. That means that guy's first digit after decimal was not 5. Let me repeat. Why is the first? Can this Cantor's number be staying in room 1? I'm claiming no. Why do I say no? Because in Cantor's number, the first digit after the decimal point is 5. But if the guy who is staying in room 1 had 5 as his first digit after the decimal point, he would have read the notice and reported to Cantor. In this case, this number would have been 6, not 5, right? So that means, yeah, the guy who is staying in room 1 does not have 5 as his first digit after decimal point. So it is not Cantor's number. Room 1 is not occupied by Cantor's number. What about room 2? Cantor's number has 2 in that position, the second position after the decimal digit. But the guy in the room 2 does not. Because if he had 5, he would have reported to Cantor and Cantor would have made this 6. So Cantor's number is not staying in room 2. Cantor's number, for the same reason, is not staying in room 3. Same reason, not staying in room 4. Room 5, let's examine that because that's where the first 6 comes in. Cantor's number has 6 in the 5th position. But the guy, it is 6 there for a reason. Why is it 6 there? Because the guy in room 5 came and reported to Cantor, which means the guy in room 5 had 5 in the 5th position, not 6. But Cantor's number has 6 in the 6th position. So Cantor's number is not staying in room 5. Similarly, Cantor's number is not staying in room 6. It's not staying in room I for any I. This is the toughest part of the argument. So I want you to take a minute and. By the way, do you have a class right after this, or when is your next class?
12 o'clock.
12 o'clock. Okay, I think I'll finish in 5 minutes. Okay, 10:30. Okay, this is the slide that you really want to understand from this talk. Okay, and if you look at the red numbers, though the font is kind of a bit narrow font, but this red numbers on the table, the third column of the table, looks like a diagonal. It's a first digit after the decimal point on the first row, second in the second row, third in the third row, fourth in the fourth row, and so on. So this looks like a diagonal. Okay, that's why this is called the diagonal argument. So as somebody asked, are there other numbers Cantor could have picked? Actually, yes. What Cantor has to do is to first pick the diagonal number. Okay, it would be something like 0.440250 in this example. For a different example, it would be a different number. So you pick the diagonal number and then change every one of them. Okay, don't retain any of the diagonal numbers. So the first decimal point, first digit after the decimal point is 4. You can place any of the other 9 digits in place of 4. Similarly, the next you can place any digit other than 4. In the third position, you can place any digit other than 0. In the fourth position, you can place any digit other than 2. In the fifth position, you can place any digit other than 5. In the sixth position, you can place any digit other than 0. All these answers, with all these numbers, Cantor could have won. Okay, so this is like you kind of take the diagonal and then make sure that nobody, every symbol in the diagonal is changed to something else. And then the same proof will work. Then you will be able to argue that that number created is not in room 1, not in room 2, not in room I for any. This is the flipping the diagonal, or the diagonal perturbation trick. You take the diagonal and then change every number in the diagonal. Okay, so I hope this is clear. There are no doubts. Okay, so this is how Cantor won. Okay, so real numbers cannot be accommodated in Hilbert's hotel in a one-to-one fashion, in a injective fashion. So indeed, the infinity of real numbers, Cantor's infinity, is larger than Hilbert's infinity. Cantor actually made that statement during the argument, if you remember. Okay, so this is a larger kind of infinity. By the way, actually, this is a special case of Cantor's theorem. Cantor's contribution to mathematics is, so important. He actually not just showed that there is one infinity that is larger than the infinity of natural numbers. He showed that you give me any infinity, I will give you an infinity that is larger than that. Okay. So, and his idea, his example was always this: if you give me an infinite set, I'll take the power set of it. Remember what's a power set? Set of all subsets. Okay. And he proved, again, using a generalization of this diagonal argument, which I won't show today, that the power set of a set can never be assigned a one-to-one mapping to the set itself. Okay. So in fact, there are infinitely many infinities. Actually, the power set of natural numbers and real numbers happen to be the same size infinity. They can be fitted into each other. But if you want a further larger infinity than real numbers, you can look at the power set of real numbers. That will give an infinity that is even larger than the infinity of real numbers. These infinities, by the way, have symbols. They are called Aleph naught. Aleph naught is the symbol used to denote the infinity of natural numbers. Aleph 1 is the one used to denote the infinity of power set of natural numbers, which is same as the infinity of real numbers. Aleph 2 is the power set of that, which is further. Then you have Aleph 3, Aleph 4, and so on. So there are infinitely many different sizes of infinities. Okay. So yeah, so let's end this with a pop quiz. Okay. So yeah, so there are 3 quotations here, and I want you to don't Google it now, but I want you to see if you can guess who made these statements. Okay. The first says, the first 2 quotations, by the way, this Cantor's discovery of this infinitely many infinities and so on was almost like the discovery of irrational numbers by Hippasus. Okay? The mathematicians at that time, when Cantor made this discovery, were kind of divided into two opinions. Some guys thought Cantor was just imagining things, cooking up. This is not real mathematics, and so on. There were others who thought actually, who saw the genius of Cantor and was in praise for it. Okay. So the first quote says, infinity is nothing more than a figure of speech. So it's trying to completely kind of humiliate Cantor. It tells, okay, it helps you to talk about limits, but it does not belong to mathematics. Okay, this says a notion of a completed infinity, it doesn't belong in mathematics. Okay? And this statement is, I picked it because this is by probably the most famous mathematician of all times. He's called the Prince of Mathematics. Who is known as the Prince of Mathematics?
Gauss.
Gauss, right? So this first statement is by Gauss. So even Gauss had a difficult time accepting Cantor. The second, I don't know what predominates Cantor's theory, philosophy or theology. Okay, theology is a study about God, right? But I'm sure there is no mathematics there. This is a statement by a mathematician called Kronecker. Okay. The third one, on the other hand, is very much in praise of Cantor. it says no one shall expel us from the paradise that Cantor has created. By the way, there is a website called Cantor's Paradise, which has a lot of good articles about mathematics. Okay, so this is actually a trick question. Can you guess who said this? The third quotation?
Hilbert.
Exactly. That's by Hillbert. So this entire story that I made up was just to dramatize things. And this Hillbert Hotel is known by that name. You can Google it or search it in Wikipedia. But Hilbert was one of the first people to understand the power of Cantor's idea, and he was a proponent. He was a big supporter of Cantor's idea. Okay. So this quote, which survives now. Okay. I mean, now everybody understands that Cantor made a very significant contribution to a lot of things. By the way, this diagonal argument, that spirit of that diagonal argument, you will see many times repeated in computer science. Turing used it to show that not all problems have solutions. By the way, okay, I should have said that now, right? You remember, let me try to connect two of the scenes. There was this language conference at the end of which I remarked that all computer programs can be accommodated in Hilbert's Hotel. Okay? Whereas all subsets of natural numbers cannot be accommodated in Hilbert's Hotel. So there are more subsets of natural numbers than computer programs. Okay. Now, the subset of natural numbers makes a good computer programming assignment. Okay. Like for example, if I take the subset of even numbers, the even numbers among natural numbers, I can ask you to write a C program to check whether a given number is an even number. Now, instead of even numbers, if I pick odd numbers, that becomes another assignment question, another programming assignment. Instead of that, if I take prime numbers, that becomes another programming assignment. Write a C program to check if a given number is a prime number. Does it belong to this chosen set? So I can pick any subset S of natural numbers and set a programming assignment, right? I can ask you to write a C program, which given a natural number will check whether the number belongs to S. And we saw that. So for every power set, there is an assignment question. But they are much more than the number of C programs that you can write. So I can create what are known as uncountably many assignment questions, but there are only countably many C programs. So surely there are many questions for which nobody, not even you, nobody will be able to write a C program. Okay? So not all tasks which look like which can be done by a which can be solved by a computer program can actually be done. Okay, and in particular, Turing showed a particular problem called the halting problem cannot have an algorithm. It used exactly a variant of the diagonal argument and so on. So this diagonal argument, due to Cantor, has made its presence felt in computer science in a very, very, very strong way. Okay. Now, this I have already said during the talk, right? I mean, all this story could be expressed in terms of, very formal mathematical notation. Allotment of guests to rooms correspond to a function from the set of guests to set of rooms. The rule that one guest per room, the single occupancy rule, essentially translates to the function being one-to-one. And in particular, if you're talking about Grand Hilbert's Hotel, then the codomain is a set of natural numbers. So we are talking about injective functions or one-to-one functions from set of guests to set of natural numbers. Yeah, now this is the definition of a countable set. A countable set is a set which from which you can find a one-to-one function into natural numbers. So other way to define it would be those elements which can be accommodated in the Grand Hilbert's Hotel. And so countable includes finite also, by the way, right? So finite sets are easily seen to be countable. Other infinite sets that we saw are countable included natural numbers, integers, rational numbers, set of English sentences, the language conference, if you remember, and so on. If you cannot accommodate a set in Hilbert's Hotel, then we call it an uncountable set. We saw one example, the set of real numbers. We mentioned another example, which is the power set of natural numbers, and there are many more. Okay. So if there was a sequel to this story, then it would have been the Cantor, the Grand Cantor Hotel, where you have a room for every real number. Okay. And then the question would be, can it host every conference? I already gave you the answer in the talk. So, I mean, there is no suspense there, but I want you to, do that story yourself. So, I mean, there is no suspense there, but I want you to, do that story yourself. Okay, so yeah, I'll end my presentation here. If there are any questions, I'll be happy to answer.
Sir?
Yeah.
Sir, could you just one time repeat the diagonal argument as in how that number couldn't fit inside? I understood how the number formed.
Correct. This one, right? So you understood how the number was formed. Okay. In fact, I have, in order to make it a bit concrete, I have been very specific about 5 and 6. Okay. So I'll stick to this example, just to make it clear. So do you understand that Cantor's number is not in room 7? Okay, because room 1 to 6 are already written on the table. So I want to take another example. Without even knowing what is the number in room 7, can you tell me a proof that Cantor's number is not staying in room 7? So let us say the 7th digit in Cantor's number was 5. Then what would be the 7th digit of the guy staying in room 7?
So it won't be 5 over there.
It won't be
Other than
5. So it is not Cantor's number.
Yes,
right?
sir.
Okay. Now suppose the 8th digit in Cantor's number was 6. Can you prove that Cantor's number is not staying in room 8?
Yes, so then it will be 5 over there.
Exactly. So now can you prove that for any given I being 1, 2, 3, 4, whatever, right? Any counting number, can you prove that Cantor's number is not staying in room I?
Yes, sir.
Right. And Hilbert's hotel only has these rooms, right? It only has rooms 1, 2, 3, 4, all I's that we were speaking about. And
Yes, sir.
Cantor's number is not staying in any of them. We have a proof for that fact.
Yes, sir.
Is it clear? Yeah.
Yes, sir.
Is it clear? Yeah. Any other question? Okay, by the way, this is what is known as an existential proof. Okay, in some sense, right? It kind of tells you that whatever is the argument, but let me not get into that. Okay, this is also a very good example of a proof by contradiction. The root 2 rational proof is also a proof by contradiction. This is also a proof by contradiction, which I kind of changed into an argument between two people. Okay, so the Hilbert's claim that he has accommodated every real number in a room is the first step in a proof by contradiction, where you really assume that what you are trying to prove is wrong. So here what you are trying to prove is that all real numbers cannot be accommodated in Hilbert's hotel. And we start by assuming that is false. That in fact, we start by assuming that, every real number can be accommodated in Hilbert's hotel. So what Hilbert is saying is just the first statement in a proof by contradiction. Very, very much like saying, suppose root 2 could be written as P by Q. That's the first statement in a proof by contradiction. Very, very much like saying, suppose root 2 could be written as P by Q. Okay. Yeah. So okay, let me just wind up by saying that this is also the kind of mathematics that gets very much used in computer science, because a lot of foundational questions in mathematics, like questions in set theory, questions in logic, has direct consequences in computer science. In fact, it's very difficult to disconnect these two. The only thing is that computer science, at least formally computer science came into being after Alan Turing, 1930 and so on. This is older to that, but many of the ideas are borrowed from these kind of foundational mathematics. But many of the ideas are borrowed from these kind of foundational mathematics. Okay, so any other questions or comments? If not, thank you for your listening. Right.